All right, we are now going to look at written response questions, part 1. So we're going to make a key as we go through this. Draw a Lewis electron dot diagram for an atom of iodine. So let's look really quickly. Periodic table. So the electron configuration for iodine, and we have to look at the very last number, because all I'm going to show in Lewis dot structures is valence electrons. Because look at this. This says this is how many electrons in total iodine has, 53, because that's how many protons it has. But please, please, please do not draw that many. I just look at valence electrons, and it has 7. So an atom of iodine has 7 valence electrons. So I draw the symbol, and then I draw 8 valence electrons around the symbol. I start on one side. I usually just start on the top and go around. 1, 2, 3, 4. Imagining the eye in a box. 5, 6, 7. So what this tells us is we have some pairs. These pairs will not bond. Iodine will only form one bond because it has one unpaired electron, and that's it. The next one says to draw a Lewis electron dot diagram for an ion of iodine. Well, when it's an ion, it has a -1 charge. It will gain 1 electron. So it has iodine. Instead of having 7, it will have 8. But I can't just draw it. This would indicate it's an atom. I have to do something to say it's an ion. And I have to put it in brackets and put the charge outside the brackets. Okay, say that it were magnesium, just 2 valence electrons. It is not going to gain 6. This 8 valence electrons is the octet rule. Okay, I'm not going to gain 6. That's unreasonable. So I'm going to lose 2. So when I draw magnesium with its valence electrons now, well, I don't have any to draw. But I can't just draw this because it's an ion. So I have to put something that says it's an ion, and then I put the charge. Okay. Let me just show you a few Lewis dot structures that you should know. You should know hydrogen with a halogen. So it could be chlorine, fluorine, bromine. Okay. You should know water. And water is polar because it has a bent structure. So that's water. You should know diatomic oxygen. It has a double bond. Okay. And you should know diatomic nitrogen. It has a triple bond. Okay. And one more for sure, you should know CO2. Okay. CO2 has 2 double bonds and a linear structure. So if we look at these structures, this would be nonpolar bonds, nonpolar molecule. Polar bonds, polar molecule. Polar bond, polar molecule. This would be a non-polar molecule. Now, how do I know if it's polar or non-polar bond? Remember, I'd have to do some electronegativity subtracting. So let's just double check. It would be 2.6 for carbon, and oxygen would be 3.4. Oh, that difference is polar. So this is a polar bond, and this is a polar bond. But this is a non-polar molecule because it has symmetry. Okay? This is non-polar bond, non-polar molecule. Polar bond, polar molecule. All right, that's just some other things to remember. It was not this question, but it's a good time to review it. In terms of atomic structure, why gases are unreactive elements. Why noble gases are unreactive elements. First I was like, gases? What the heck? Noble, that kind of makes a huge difference. So, oops on my reading that. So noble gases, notice they have how many valence electrons? 8. Exception, helium. Helium has 2 total. So elements are stable when they have 8 valence electrons or 2 total, like helium. So why, in terms of atomic structure, are they unreactive? They are unreactive because they have full valence electron shells. In most cases, that means 8, right? So now let's look here. We got an equation. Explain in terms of collision theory why the rate of the forward reaction decreases when the concentration of N2 is decreased. So when I decrease N2, the reaction will shift this way. As the reaction shifts this way, I use this up, make more of this, and make more of this. So why would the rate of the forward reaction decrease in terms of collisions? So the rate decreases because there are less effective collisions. Period. Rate slows down, less effective collisions. Rate speeds up, more effective collisions. All right, so here let's look at this. It says determine the total mass of oxygen that reacted. Let me tell you something. This seems like a hard question, but it is easy peasy. Ready? We have 4.86 grams of calcium, and it forms 6.80 grams of calcium oxide. So how much is this? Well, the law of conservation of mass says that the mass that we started with has to be equal to the mass that we ended with, right? So if we ended with 6.8 grams, 80, we had to start with 6.80 grams. So what I would do is take 6.80 minus 4.86, and I get 1.94. So 4.86 grams of calcium plus 1.94 grams of oxygen would yield 6.80 grams of calcium oxide. Again, it seemed like a whole hard question, but it was easy peasy. Explain in terms of electrons why the radius of the calcium ion is smaller than the radius of a calcium atom. So let's look at calcium on the periodic table. When we do, we see that calcium has 2 valence electrons and it forms a +2 ion. So why is it smaller? Because it loses 2 electrons. So the calcium ion is smaller because the atom loses 2 electrons to form the ion. Okay, carbon forms molecular compounds with some elements from group 16. 2 of these compounds are carbon dioxide and carbon disulfide. Here's a bunch of information. It says identify one physical property and one chemical property of CS2. I promise you this is in the reading. Like, no one is asking you this weird random question. So go back. Carbon dioxide is colorless, odorless, but I want to describe this, so that doesn't help me. So I'm going to keep reading. Finally, carbon disulfide is formed by the direct reaction of carbon and sulfur. At room temperature, CS2 is a colorless liquid. Physical property, colorless liquid. Okay? With an offensive odor. That's also physical. Carbon disulfide vapors are flammable. Aha! chemical property, flammable. If you try to burn something, you change it, okay? State what happens to the potential energy of CO2 molecules during this phase change of CO2. All right, so it says CO2 changes directly, CO2 solid. So I went from a solid to a gas, right? At STP, CO2 solid changes directly to CO2 gas. So state what happens to the potential energy. If I'm going from a solid to a gas, the potential energy increases. So does the kinetic, okay? Because I'm following the path of a heating curve, right? Compare the intermolecular forces in CO2 and CS2. So in order to compare intermolecular forces, some information that helps is boiling point, but I don't have it. But what I do know is that at STP, carbon dioxide changes directly to a gas. And at room temperature, CS2 is a liquid. So if at room temperature CS2 stays a liquid, that must mean it has stronger intermolecular forces. So CS2 has stronger intermolecular forces because it's being held as a liquid, whereas CO2 is a gas that goes straight from a solid to a gas. All right, now for this question. All right, this question right here, draw a structural formula for butane. So I need to go to the reference table to remind myself if you forgot. So always double check if you aren't sure. But means a chain of 4 carbons, and ane means it is an alkane, right? Which means it has all single bonds. So butane should look like this. A chain of 4 carbons. Each carbon must have 4 bonds. So that would be done. Or I could do this. Still do the same thing, but at the end of every line, put an H. Okay? So it would be like that. Okay? Now, this one, at STP, which alkanes are liquids? So notice these temperatures are all given in degrees Celsius. So the STP value that I want from this table is 0 degrees Celsius. So STP is 0 degrees Celsius. So here's what you should know, that we have melting point, we have boiling point. Below the melting point, we are a solid. In between melting point and boiling point, we are a liquid. And above boiling point, we are a gas. Okay? So that means, for example, if I had a boiling point of -10 degrees Celsius, for example. So where would 0 degrees be compared to this number? Well, it would be over here, right? It's bigger than that number, so I would be a gas. Okay? So what I need is I want to be a liquid, so that means I can't have boiled yet. So I need something greater than 0 degrees Celsius. Because if I look here at this big negative number, at 0 degrees Celsius, well, it's already boiled. It's like, that's way warmer than that, right? It already boiled. At 0, this already boiled. So did this, so did this. So what's left? Which ones did not boil? Right here. So this would be pentane, hexane, heptane, and octane. Now this should make sense because as the number of carbon atoms increases, the intermolecular forces increases. So these are liquids instead of gases because they have stronger intermolecular forces. Okay? All right, now let's... All right, now we're on this question. What is the boiling point of propane at 1 atmosphere in Kelvin? So we have to get it in Celsius. So here we have propane, the boiling point in Celsius is negative 45 degrees Celsius. So how do I convert it to Kelvin? Well, I have my reference table and here's my formula. So I'm going to write that down. K equals degrees Celsius plus 273. What do I have? Right now I have it in degrees Celsius, so I'm going to replace this with this number. K equals negative 45 plus 273. If you don't know how to do that, use a calculator. Be careful. You have a calculator, you can use it, right? So let me just turn this so you can see it. There we go. So 45, I've read up the negative. Negative 45 plus 273 equals 228. So my answer, 228 Kelvin. Now I have a bunch of reading, and then I have this question. The volume of the piece of magnesium is expressed to what number of significant figures? So here's the magnesium, here's its volume. How many significant figures? Well, there is a decimal, so that means I start on the left side, skip this 0, skip this 0, count, count, count. So 3. Show numerical setup for calculating the volume of the H2 gas produced as the conditions are changed to STP. Where do I find STP values? Remember, right here. Okay. Now, if I look through this, I see no mention of temperature. The formula I use is P1 V1 over T1 plus P2 V2 over T2. But temperature isn't even mentioned in the problem. It's not asking me for temperature. It doesn't tell me a temperature. So that means get rid of it. So I'm just left with P1 V1 equals P2 V2. Now, hydrogen is what I'm doing this for. Okay, so let's see what I start with. What's the pressure that I start with? Oh, 1 atmosphere. 1.00. What's the volume? 112 milliliters equals, and the condition, and oh, I take it back. Look at this. We do have a temperature. So let's put this back in my formula. Sometimes that happens. Is the temperature in Kelvin? Beautiful. Keep it. 298 K equals. Now here's where I change it to STP. So the P2, V2, T2 are going to be STP. So my pressure was in atmospheres. So STP in atmospheres is 1. Well, that didn't change. Okay. V2 is what I'm trying to find. But what is temperature in Kelvin STP? 273. This is it. Stop. When it says show a correct numerical setup, stop right there. Done. Finished. Go no further. Bzz. Okay. This question is not going to be on your paper when you get it printed, so we're just going to ignore it. Let's go on to this question. Identify 2 differences in the structures between a molecule of butanoic acid and a molecule of ethanol. Each of your responses must include both compounds. Whew, okay, so I have to figure out what butanoic acid looks like and a molecule of ethanol. Okay, so anol, anoic acid, but, F. Okay, so I have to just say both. So butanoic acid has 4 carbons in the chain, but ethanol only has 2 carbons. Okay, there's one difference. Now I need a second one. The functional group for ethanol is OH, but the functional group for butanoic acid is COOH. Okay? Identify the type of organic reaction that produces the compound that contributes to the odor of pineapple. Well, look at this. This says ethyl butanoate is an organic compound that contributes to the odor of pineapple. Let's go back to table R and let's look. Let's look for something. Oh, right here. Look at this. Methyl propanoate, same pattern. It's an ester. So the type of organic reaction that would produce that. What kind of organic reaction makes an ester? Esterification. Remember, the organic reactions are PS bases. Polymerization, saponification, fermentation, addition, combustion, esterification, and substitution. All right, identify one ion from table F. So please, for the love of Pete, go to table F. That can combine with Pb plus 2 to produce an insoluble compound. Okay. So I have some special guests right here. Do you see this? So that means all of these are soluble, but if it's with Pb 2 plus, it is insoluble. So Cl, Br, I, SO4. Those would all work. Okay. Also, what would work are these ones where Pb doesn't break its rule. They're insoluble. So it could be anything over here. It could be one of these. I'm going to pick Cl negative. Okay, you got a lot of choices there. Describe one appropriate laboratory test that can be used to determine the malleability of a solid sample of an element at room temperature. So you could hit the metal with a hammer to try and flatten it. If it breaks apart, it is not malleable. State 2 methods to increase the rate of a chemical reaction and explain in terms of particle behavior how each method increases the reaction rate. Okay, so we can add a catalyst which lowers activation energy and provides an alternate path where there are more collisions. That's one. Now I need a second one. Okay, so I can increase temperature. Those are my two go-tos. Add a catalyst and increase temperature. That changes rate. So increase temperature, which causes particles to move faster and collide more often and with more energy. Okay, our last question on this page has a bunch of parts. Okay, state in terms of subatomic particles how an atom of copper-63 differs from an atom of copper-65. Copper 65 has more neutrons. Copper 63 has less neutrons. Copper 65 and copper 63 have different numbers of neutrons. What is the total number of electrons in this atom? Well, that 65 is unimportant. How do I determine the number of electrons? Go to the periodic table. Since copper has 29 protons, it has 29 electrons. 29. The atomic mass of copper 63 is expressed to what number of significant figures? Atomic mass, copper 63. How many significant figures? Well, there's a decimal, so we start on the left side and count everything. 1, 2, 3, 4, 5. And show a correct numerical setup for calculating the atomic mass of copper. So what I have to do is change the percent to a decimal, which means I move the decimal 2 places over. So this is 0.6917, and this is 0.3083. And what I do is I take 0.6917 times 62.930, add that to the second one, 0.3083 times 64.928, and that would give me my answer. Another way to write this, which I have seen a couple times, is if we don't do this first, I would take 69.17 times 62.930 plus 30.83 times 64.928, and then divide it by 100. This gives me the same result as these two, but sometimes if they already give you a numerical setup, it might look like this. Now when I get my answer, just as a little fun fact here, if you look at copper's atomic mass, it is 63 point something. So it is between these two numbers, which makes sense. You can see that there is more copper 63, so it makes sense that it's closer, the answer is closer to copper 63. So that's just logic, okay? All right, that is the end of part 1.